Hi, everybody, and welcome back to our lecture series on statistics. In this particular lesson, we're going to talk about frequency distributions and graphs. Then I'm going to show you how to calculate frequency distributions by hand. All right, so let's get started. In order to ground us, I would like to explain why we do frequency distributions in general. And the first and primary reason that we do frequency distributions is that it helps us organize the data in a more meaningful way. It helps us go from a raw score to a summary score in a pretty aesthetically pleasing way. So let's say I asked you, how stressed have you been in the last 2.5 weeks? And I asked you to rate this on a scale from 0 being not stressed at all and 10 being as stressed as possible. Well, if I were to just give you all 151 data points or scores, that's not very efficient. It's not aesthetically pleasing, and it's very hard to identify any patterns that might emerge. So we have a frequency distribution, and the way we do this is we list all the numbers from highest number to lowest number. So in the case of stress ratings, the first number up would be 10, and you do 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and that would be in the X column. And then if we were to calculate frequencies by hand, we would just count how many 10s there were, how many 9s there were, how many 8s there were, and so forth. And you could do this by cancellation or tick marks, however you want to do it. But let's say this was a resultant graph, right? So instead of having, just 151 data points, it's much easier to read something like this. So we can see the stress ratings, right? So, and then in the stress ratings column, that would be analogous to your X column or your score, right? And then in the F column would be frequency, because the symbol F represents frequency. You would have however many times 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1 or 0 occur. Now, we also do cumulative frequencies. Cumulative by definition means to add, it's additive. So when we do a cumulative frequency column, we actually start from the bottom and work our way up. And I will show you what I mean shortly, but cumulative frequency is used to help calculate where the median was. It could help you determine how many scores are below whatever we're looking at. It could help us calculate percentiles. And in fact, my next lecture in the lecture series is all about calculating percentiles, percentile rank, and so forth. So if I were to give you guidance, I would say, well, step-by-step procedure would be as follows. So list every score or every value for an X column, right? X represents a score. And then you start at the highest number and work your way down. And then you do your F column, which is your frequency column. And then you start at the bottom and then you add to it, working your way up. And then you continue that process until you get to the top of the distribution. So if I were to look at the CF column, right? CF stands for cumulative frequency. right? We already had, if I go back, we already calculated the stress rating and the frequency. Now we need to calculate cumulative frequency. And if you look what I said in that third bullet point, we start at the bottom of the column and then add to that. So cumulative frequency, this one where you see my cursor moving is where we would start. So the frequency, now obviously we start with 0. 0 plus 2 gives us 2. So at the bottom of the distribution, you're going to have 2. Now, you'll notice that we're going to work our way up the cumulative frequency table, right? So 2 plus 1 gives us 3. 3 plus 3 gives us 6. And all I'm doing is adding whatever number is here with the next one up. So 6 plus 12 gives us 18. That 18 plus 16 gives us 34. 34 plus 18 gives us 52. 52 plus 13 gives us 65, and so forth until we get to the 151 participants. As you may recall at the beginning, that was the number of participants in the stress study. So if we were to add up the frequency column, we would get 151. The bottom of the F column should add up to the top of the CF column. And so let's just go to start to interpret CF, right? So CF, if I were to go to this CF stress value for 5, so we have 52. What does that 52 mean? Well, that 52 means, because it's cumulative, there are 52 participants in my study that have a stress rating of 5 or below. Listen to what I said. Because it's cumulative, we added our way up. The CF of a stress rating of 5, if I go all the way across, was 52. That is to say there are 52 participants who had a stress rating of 5 or below. Now, let's do the same thing for 9. So I'm going to find my stress rating 9 and go all the way across to the CF. And now my cursor is there, and it says in the CF column for 9, it says 137, right? So 137 respondents or members of my survey had a stress rating of 9 or less. And that's how you interpret cumulative frequency tables. Now, what I would like to do is take a moment and do this in a Word file to show you how you would calculate the CF column. Now, let me pull up a Word file that I made. And again, my goal when I do this is not to make it hard, but it's just to highlight a point. So right now, and only now, I am going to work with this small data set. So let's put this up, and I notice I use some measure that they rated from 1 to 3. Now, if I were to ask for the cumulative frequency, I would start from the bottom, and you see how it's blinking there? Well, I would bring that 2 over, right? Because 0 plus 2 gives me 2. Now, the next number up is 4. So if I want to get the cumulative frequency, working my way up, I should do 2, which was the number in the CF column, plus the 4 that's in the F column. And that would give me, 1 second, that would give me 6, right? So that is how I got it. Again, this 2, the bottom 2 in the CF column, plus the first 4 in the F column gives me 6. Now, because it's cumulative, we're working our way up and we're adding. So now we're going to work our way up with the 6 in the CF column and add 4 to it, right? So 4 plus 6 would give us 10. Now, I said to you that the top of the CF column, which is 10, and I'm going to bold that, should add up to the bottom of the F column. So why don't we add 4 plus 4 plus 2? 4 plus 4 is 8, plus 2 is 10. And sure enough, we have our match. So I'm going to bold that. So adding the F column, we got 10. It should match the top of the CF column. You should get 10. Now, I did this by design, and you'll notice I wanted it to be mathematically easy because I'm just teaching a principle. But that's how it would work if you're doing it by hand. Now, I am going to come to the percent and the cumulative percent, which is abbreviated as C%, in a minute. But let me go back into our slideshow and we'll get there. So here we were talking about how we got there. Again, go across from the bottom, 2 gets brought over, 2 plus 1 gives you 3. So the 2 of the bottom CF plus the next number up in the F column gives you 3. And then you just add your way up, sort of zigzagging. All right. Now, sometimes we have larger data sets and we may not use individual scores. There's something called a grouped frequency distribution. And when we do a group frequency distribution, we're taking multiple scores and putting them into the same class, right? Into a single interval. One criticism when you use a grouped frequency is that it becomes less precise than a regular frequency distribution. And the common scenario where people do it, and I always say that there's a much better way, is with age. We ask people to pick their age group, 18 to 25, 26 to 44, 45 to 64, and so forth, right? So people are put into age categories, but we might know which category you belong to, but we wouldn't know your actual age. So that is the biggest criticism. Now, there are other studies that use group frequency distributions, like the Morehouse and Sanders study in 1992. They looked at children's attitude towards learning and work. They had 153 people, and then they clustered it together. Now, in this particular case, we want to understand what interval width is. So interval width, symbolized by the lowercase letter I, is the relative size of the interval. And when we talk about group frequency distributions, we should have intervals of 2, 3, or 5, or multiples of that. And depending on how large our data set is, the number of options or intervals should be anywhere between 8 to 15, no more than 15. And make sure whatever your interval size is, the bottom number is counted as a number in that interval. All right. So here would be that attitude towards education and work. And you'll see that it has a series of intervals. Let's see if it follows the rules we talked about. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 in intervals. Now, what is the interval width? Well, logic would tell you that you take the largest number and subtract the smallest number from it. However, if you remember what I said, the smallest number counts as one of the numbers in the interval as well. So let's take 20 to 29. What's 29 minus 20? 9. But because the smallest number counts as one of the intervals, one of the scores for that interval, we have to add 1 to it. So 9 plus 1 is 10. So believe it or not, the interval width is 10. Now I'm going to show you this, right? I said the smallest number counts as one of the numbers in that range of scores. 120, 121, 122, 123, 124, 125, 126, 127, 128, 129. So notice it is indeed 10 because 20 would be one of the numbers. All right, so the interval width would be 10. Is 10 a multiple of 5? Sure, right? 5 times 2 is 10. So it keeps that rule. And the number of intervals presented, we said were 11. So we're in within all the rules we said. Now, if we were going to calculate other statistics, there are other ones that you'll see reported in research studies. You might see proportion, you might see percentage, and you might see cumulative percentage. So proportion is simply the number of cases in a given class divided by the total number of cases. That's going to be your proportion. Now, if we want to do that, that's always going to be a decimal. So when we do percentage, it's basically proportion times 100. So frequency of a score divided by the total number of scores times 100. And then cumulative percent is adding up the percent the same way we did with the frequencies. Now, I said that we should be able to do that with our data set too. So let me go back into that Word file, right? So here we are, right? And we're gonna do our percents. Now, the formula was F for frequency divided by N, which is the total number of participants, times 100. So in this case, 4 divided by 10 is 0.4 times 100 gives us 40%. We do the same thing for the next one. 4 divided by 10 times 100 is, again, 40%. And again, it probably should not be bolded. There's no reason to have it bolded, right? And then the next one, 2 divided by 10 is 0.2 times 100 gives us 20%. Now, if I had a full distribution, this all should add up to 100%. So let's see if that worked out. 40 plus 40 is 80, plus 20 is 100%. So far so good, that works out. And then when we do C percent operates very similar to our cumulative frequency, right? So we start at the bottom. So we're going to bring that number over, and that would be 20%, right? And 20 plus 40, again, we're doing this staggered approach. 20 of the C percent plus the next one up, 20 plus 40 is 60%, right? Now, 60 plus 40 gives us 100%. And similar to the bottom of the F column, the bottom of the percent column should match the top of C percent. So indeed, our 100% right here adds up to our 100% at the top there. So that would be how you would calculate frequencies, cumulative frequencies, percent, and cumulative percent by hand. I will make a different video in which I show you how to calculate frequencies using SPSS, but I think that should be a separate video. All right, so if you're going to graph your scores, another thing I want to talk to you about, because you're going to see this in research, is that the independent variable or the grouping variable or participant variable always goes on the x-axis, and then your frequencies, which is commonly your dependent variable, goes on your y-axis. All right, so here's a graphic representation. So you have your categories on the x-axis and then your frequencies on the y-axis. Now here are proportions. Now remember, proportions is F divided by N. It's not the same as percentage, right? Because percentage should be whole numbers. They could have multiplied this by 100 to get whole numbers. All right. So your x-axis has your participant variables or your categories: married without children, married with children, single mother with children, single father with children, and some other family structure. And on the relative frequency, this is our proportion. So roughly 42% of the population is married without children of, this particular data set, right? Then we had about 36% married with children. And then the single parents are much more infrequently, but they still occur. All right, so this is a bar graph. Now, there is a difference between a histogram and a bar graph, or there are several. A bar graph or a bar chart, each category is separate and distinct. So you can't be married without children and married with children at the same time. You can only fall into one category. So because the category that you put yourself into, you can only land in one, the bars are separated, right? So an alternative to a bar graph is a pie chart, and you could get the same kind of idea. Now, if your dependent variable is interval ratio and your measurement variable or your independent variable is continuous data, usually like stress ratings, it's continuous from 0 to 10, like we said previously. Then you're going to use a histogram, right? Because a histogram is designed for continuous data, which is a fancy way of saying that the variable of interest is either interval or ratio in nature. So the stress, there are units from 0 to 10, but the response choices were in units of 1. So now in a histogram, because you're using scale data, the bars are going to touch and they're no longer distinct categories. And then still though, in the y-axis, you have your frequency, right? Number of participants who identified with a given stress rating. So there are other ways to do this. Again, one of the tricky things we had with grouped frequency distributions, right, you may remember, was that it loses sensitivity. But there is a way, if you wanted to represent each individual score, so it keeps its sensitivity, and that's called a stem and leaf diagram or a stem and leaf display. So you may recall that the ratings in Morehouse and Sanders went from 20 all the way to 129, right? So 20 to 29, 30 to 39, 40 to 49, and so forth. But there was one person in that 20 to 29 category. So, but what was their score? We don't know. If we go back, there was one person in the 20 to 29 category. We don't know when we look at a group frequency table, but we would know if we turned it into a stem and leaf diagram, right? Because we could do the stem in units of 10 and the leaf in units of 1. And then we would just take the tens place and the ones place, and that would tell us what that number was. So there was one person who was 20 to 29. If we put the 2 and the 5 together, what do we get? 25, right? So that score was actually 25. And there were two people who got scores in the 30 to 39 category. Well, we do the same thing. Let's take the tens place and the ones place. 3 and 0. First score was 30. 3 and 2. Second score was 32. And so forth. But it's fascinating, isn't it? Right? You could actually identify the numbers even with a group frequency using a stem and leaf design. Now, so we have our frequency polygon, which is instead of using a bar graph, right? So we talked about those stress data, right? So the bar graph, it was, pardon me, the stress data was a histogram, right? How many people said 0 stress level, 1, 2, 3, 4. Now, a frequency polygon is another way of depicting the same display as a histogram. So if we go back, I want you to take a look at this shape, right? And go back. It's actually the same shape as the histogram because it's the same data, right? So this is in a bar-based form, and this is in a line-based form, right? So again, frequency polygons are used for interval and ratio data or continuous data. The scores get put on the x-axis, and the frequency or frequency counts get put on the y-axis. And that's how you would do that. Now, a cumulative frequency distribution, in general, we have a, actually, I want to say something else about this, forgive me. In a regular frequency polygon, notice the line goes up and down, right? Because it's based on the frequencies of a given score. When we talk about cumulative, the definition of cumulative means additive. So we're adding 2, which means that as we do a cumulative frequency polygon, the scores are going to either increase as we move across in the data set or stay the same. Now, how would they stay the same? Well, let's say we had a frequency of 24, right? And then the next one up was 0. Well, 24 plus 0 stays 24, right? And so it would at least stay the same. So this is why in a cumulative frequency polygon, the line is going up. So the frequency in the y-axis cannot go down in a cumulative frequency distribution. The next thing I want to talk to you about is symmetry. So if we were doing research, we want our data to be symmetrical. That is to say, we want them to be mirror images, right? So if we were to take half of our distribution, fold it on the other half, it should approximate a bell curve. It should be a normally distributed shape. When you have a symmetrical distribution, the mean, median, and mode will all be the same. Remember that, write that down. But when you have a skewed distribution, the average gets shifted towards wherever the extreme scores are. So if we have a negatively skewed distribution, the average is pulled down to the left or down and to the left by a few low scores. So let's say I had a really easy test, right? But a couple people did poorly, that's going to pull the class average down. So the average is actually lower than the median. The mean is actually lower than the median. A positively skewed distribution is the opposite. So here we have an extremely difficult test, and our average is brought up or pulled up by a few people who did well. So note that the skew follows the tail. All right, modes. So instead of looking at the ends, we look at the top or the peak. So the mode is the most frequently occurring score. And in a form of a shape, it's how many peaks you have in a distribution. Now, you can have an amodal distribution, which is flat and no peak whatsoever, and each score is roughly identical. You could have a unimodal distribution, which has one peak, and you could have a bimodal distribution, which has two peaks and so forth. Now, the peaks don't have to be at the same height, but it just has to be sort of like one's going up and then it goes down and then it goes up again and then down. So that would be a bimodal distribution. We have two clusters of scores or two peaks. We tend to see that in teaching in undergraduate courses that many of the data sets land in a bimodal distribution. All right, so we talked about the symmetry of a distribution. We talked about the peaks of a distribution. Well, in a normal distribution, also referred to as a bell-shaped curve, the goal is that it should be unimodal, one peak, and symmetrical. And if that happens, you have a large number of scores in the center, and as you move to the sides, you get fewer and fewer numbers of scores. You could also get, though, a rectangular distribution. Now, a rectangular distribution is amodal. Amodal because that means roughly the same frequency across. That would be analogous to rolling a die and counting the probability of getting a 1 versus a 2 versus a 3, 4, 5, or 6, right? If you roll enough times, you're going to see the probability is about the same. But you could also have a J-shaped curve where it starts off slow and ramps up. And there are many different distributions. And that, in a nutshell, is our lecture. So I am going to do a separate video on how to do a frequency distribution using SPSS, but that's going to be separate. All right, let's stop here, and I will see you next time. Take care.